Hello, good morning everyone. This is Nirmalya Ghosh from Indian Institute of Science, Education and Research, Kolkata, India. First of all, I would like to thank the organizers of ISOT for inviting me to deliver a lecture in this wonderful conference. It is of course a great pleasure and honor for me to deliver a lecture here. I would of course have loved to come in person to attend this conference. Unfortunately, due to this pandemic, I could not travel. Anyway, it is really a pleasure for me to talk about our work in this conference. So let me just share my screen first. So what I will be talking on is something I have written the title here, weak measurements on spin orbit photonic effects. So weak measurement, of course, is a quantum mechanical concept, but this can be realized in the classical optics domain. And I have also made a statement here. So coupling between the spin and orbital angular momentum degrees of freedom of light manifest in a number of exotic spin orbit photonic effects, opening up a new paradigm of photonic devices for control and manipulation of light at nanometer length scale. So this is what I'm going to explain in the next half an hour or so. And in this context, I'll talk about weak measurements or weak value amplification to amplify these spin orbit photonic effects. Before that, let me quickly introduce our institute and our research group. So our institute is Indian Institute of Science, Education and Research, Kolkata, IISER Kolkata. So this is situated at the eastern part of our country in India. I have marked it here. And this institute was established in the year 2006. So it is basically a relatively young institute by, of course, the Ministry of Human Resource Development of Government of India. So the idea of this kind of institute is to promote science, particularly interdisciplinary research. And another goal of this kind of institute is to encourage students to participate in research at a young age. So that is another important aspect of this kind of institutes. So our research group, which is we call Biooptics and Nanophotonics Research Group. So I just briefly talk about our theme of research, which is mainly in the domain of nano-optics, and the spin orbit photonics, which I will be talking about, is the main theme of research in this area. We also work on the so-called plasmonics, surface plasmon resonance or localized plasmon resonance in metal dielectric interfaces and metal dielectric structures. And these quantum weak measurements, the use of weak measurements in classical optics and in plasmonics. So that is another area that we are working on. So the aim is to develop spin orbit photonic devices, some of which I will discuss today, optical sensors, weak measurement devices, etc. So polarization optics is an area that we focus our research. We work, of course, to development of various novel experimental system, polarization algebra, Muller's, Jones matrix, Stokes vectors, etc. And we try to use this polarization optics, of course, in the domain of nano optics and spin orbit photonics. And also we work on bio and interdisciplinary photonics. So this is an area where we try to develop novel optical, spectroscopic and imaging methods for characterization of biological tissue and other complex systems, right? So with this, and of course, this is our group. There are current PhD students, Athira, Niladri, Samuel, Jivan, all of them have contributed to the work that I'm going to discuss today. We also have many former PhD students. And of course, another thing I was talking about our institute, another strength is that a lot of undergraduate students, they do participate in research in our laboratory, and they have also contributed to our research. We do have a lot of collaboration in our department, that is physical sciences, in other departments like chemical sciences, biological sciences, etc. And we also have many other collaborators in India and abroad. Okay, so let me go to the outline of my lecture. So I will first briefly introduce spin orbit interaction of light and the spin orbit photonic effects. And then I will talk about optical weak measurements and weak value amplification, specifically use of this weak value amplification of spin Hall effect of light or spin orbit photonic effects. And then I will give two examples of weak measurements in the domain of plasmonics, the natural weak measurements using Phenol resonance that I will also discuss in this context in plasmonic systems, in a kind of a plasmonic metamaterial. And finally, I will talk about some new device concept using spin orbit interaction of light. So geometrical phase gradient metasurface, geometrical phase polarimeter, and weak value polarimeter. So with this, let me just briefly describe that we all know that light beam can carry both spin angular momentum and orbital angular momentum. Spin angular momentum is of course related to the polarization of light, specifically the circular or elliptical polarization of light. So circularly polarized light, left or right circularly polarized light, can carry angular momentum of plus h cut or minus h cut per photon, and also elliptically polarized light whose helicity sigma will lie between -1 and +1, so they also carry spin angular momentum. Classically, the spin angular momentum density of electromagnetic field is defined like this in terms of E cross E star and H cross H star. So in addition to spin angular momentum of light, light can also carry orbital angular momentum. This also many of us know that this is associated with the phase front, that is variation of the phase in a transverse plane. So in a symmetric system, if it varies like what I have noted here, e to the power IL phi, if it is azimuthally symmetric like that, it has a helical phase front or azimuthal phase gradient, then we call it the intrinsic orbital angular momentum. So it can have values L is equal to +1 or -1, +2, -2, and so on and so forth. Whereas it can also have extrinsic orbital angular momentum. As I said that any variation of the phase in the transverse plane is related to the orbital angular momentum. So this extrinsic orbital angular momentum is related to the symmetry breaking. For example, if I talk about a Gaussian beam, so Gaussian beam is perfectly symmetric, and if you integrate the total transverse momentum, which is defined by like this E cross B, and then if you have a y component of that, so this is like the pointing vector. If you integrate it over the entire beam, so it will vanish. Similarly, if you take the other transverse component, that is px, that is the pointing vector x component of the pointing vector, if you integrate it over, it will vanish. But for a truncated beam, like if I break the symmetry of the system, then these two will not vanish, and then we'll also have extrinsic orbital angular momentum. And I will discuss that how the different conversion between this spin and orbital angular momentum leads to interesting effects, and how you can use this for device concepts. So with the spin orbit interaction, the geometrical phase is intimately related. Yeah? So of course we know that the geometrical phase is determined by the trajectory of the evolution of the electromagnetic wave. It is not related to the path length or a material property like in dynamical phase. So these are the two variants of the geometrical phase that we will be talking about. One is the spin redirectional Very phase. So of course it was discovered by Michael Very in the context of evolution of the quantum states. Then he realized that classical light beam can exhibit this kind of geometrical phase, particularly polarized light. So this particular example I am showing here, if you have a polarized light, let's say linearly polarized light, propagates the twisted optical fiber. As it propagates, if I go along this fiber, you will see that the polarization will rotate, and it will rotate by the twist angle, right? So if it is theta, so it will depend upon the twist angle. So any such rotation, we know that if it is an optical rotation of linear polarization, is necessarily interpretable as a phase difference between left and right circularly polarized light, right? So this can be represented as that a phase difference of left and right circularly polarized light. So a phase difference of 2 theta between them will give a rotation of polarization of theta. So this theta, which is dependent on left and right circularly polarized light, is the corresponding geometrical phase, right? It does not depend on the path length and does not depend upon the material property also. It only depends upon the twist angle of the optical fiber. So this is one variant of the geometrical phase. The other variant of the geometrical phase, of course, discovered earlier by Pancharatnam, now known as the Pancharatnam Very phase. The simple example is that if I take a half wave plate, in a similar way, like I was giving the example of an optical fiber, in a half wave plate, if I rotate the half wave plate, and if I have an input linearly polarized light, depending upon the orientation angle beta of the half wave plate, the output polarization will be rotated. Again, such a rotation of polarization can be interpreted as a phase difference between right and left circularly polarized light. This can be understood by this. If I write the Jones matrix of a half wave plate like this, cos 2 beta, sin 2 beta, sin 2 beta minus cos 2 beta. So it is basically beta is equal to 0, this is 1, 0, 0, minus 1. So this Jones matrix, of course, depends upon the beta. So now you see that if I have a left circularly polarized light, 1 minus I, or a right circularly polarized light, 1 I here, the output will become flipped, that is left will become right, just like what half wave plate does, but it comes up with an additional phase factor twice I beta. It is about twice I beta. So this beta is clearly independent of path length and the material property, and therefore this 2 beta can be called as a geometrical phase. And this is Pancharatnam berry phase. So any anisotropic medium, when light propagates through it, so it acquires a geometrical phase depending upon the orientation angle of the anisotropy axis. So this geometrical phase is at the heart of the so-called spin-orbit interaction of light. So spin-orbit interaction of light deals with the interconversion between the spin and orbital angular momentum degrees of freedom. So geometrical phase, as I said, that any orbital angular momentum is associated with a phase structure in the transverse plane. Now, since geometrical phase depend upon the spin, that is input spin of the light, so it gives a coupling between the spin and the orbital angular momentum degrees of freedom of light. So to be specific, the orbital angular momentum depends upon the geometrical phase gradient. That means spin-orbit interaction depends upon the geometrical phase gradient, either a spatial gradient or a momentum domain gradient. So let us take the simplest example. So this is what we call in a symmetric system. So this is we call the intrinsic spin angular momentum to the intrinsic orbital angular momentum conversion. So this leads to spin dependent vortex formation. So most general example of this is the so-called Q plate. Nowadays we have that a half-wave plate whose anisotropy axis is structured. We know that a half-wave plate has a usually we have a fixed anisotropy axis. But if you can make that this anisotropy axis very spatial in the transverse plane, then we have something that spin-orbit interaction, because then you will generate space-varying geometrical phase, and that space-varying geometrical phase will generate the orbital angular momentum. Because it is coming through this geometrical phase, then it will couple spin and orbital angular momentum. For a symmetric system, so this will lead to a gradient, azimuthal gradient of geometrical phase, lead to an orbital angular momentum like this, del del phi. This phi d phi is the azimuthal geometrical phase, so it will give an intrinsic orbital angular momentum. So as I said, that Q plate, which is a space-varying anisotropy medium, is an example of this. We and others have shown that tight focusing or scattering can also lead to similar kind of spin-orbit interaction, because in this case also, in tight focusing or in scattering, you have polarized light in trajectory, which leads to generation of spin redirectional berry phase. Unlike this is of course Pancharatnam berry phase, but the effect will be similar. So this is actually one kind of effect, very simple kind of effect, that where you have a conversion between intrinsic spin to intrinsic orbital angular momentum. The other effect is more interesting, which is related to the symmetry breaking. So if you break the symmetry of this system, so if you have a geometrical phase gradient which is not azimuthally symmetric, so this will lead to spin dependent splitting of light beam or circular polarization dependent trajectory of the beam, which is known as the photonic spin-Hall effect. It is like the spin-Hall effect of electrons, but in case of the photons or light beam. So this is an example of conversion between intrinsic spin angular momentum to the extrinsic orbital angular momentum. Here I have shown a picture of our own experiment where you have a kind of a meta surface where you have a spatial gradient of geometrical phase. This spatial gradient of geometrical phase leads to different trajectories for left and right circularly polarized light. Or if you have a linearly polarized light, it will lead to separation of left and right circularly polarized component, which is the photonic spin-Hall effect. So recently, actually, a number of such interesting effects are observed. Similar to photonic spin-Hall effect, we have rotational Doppler effect, optical Rasva effect, plasmonic Aharonov-Bohm effect, quantum spin-Hall effect, spin momentum locking. So these all have completely opened up a new paradigm of photonic devices. So that's what I have stated here. Novel spin orbit photonic devices. So all are related to the tailoring the geometrical phase of the system, spatial or momentum domain geometrical phase, if you can tailor. So they can be used to devise multifunctional optical elements, filters, modulators, switches, sensors, isolators, etc. The advantage is that these kind of devices, because they are basically based on geometrical phase, they are mostly dispersion free. That means they are wavelength independent. They can be tuned. They are flat and ultra thin and can be integrated to a chip. So these are the potential advantages. But of course, there are emerging challenges. So challenges are there because most of these effects are very weak, typically in the sub-wavelength domain. So this enhancing the rather weak spin orbit photonic effect is one of the challenge. And of course, to gain quantitative understanding and control. So that is also another important thing for the device application. You have to have control and tunability. So these are the challenges, and of course, the avenues that are being followed is to tailor giant spin orbit interaction by tailoring large spatial or momentum gradient of geometrical phase. Like, for example, I have shown some pictures here which we have developed. I will discuss some of those. That if you can spatially tailor in the nanostructure or in the nanoscale, then you can generate a very large gradient of the geometrical phase, which lead to giant spin orbit interaction effect or giant spin-Hall effect, you can tell. right? So another avenue is that spin orbit interaction effects in hybrid metamaterials. So they are basically hybridization of different modes and resonances gives you the desired control and tunability of the spin orbit interaction effects. So I'll give example of both these two. And then also you can combine nanostructured metamaterials with structured light. So this is what I will not be talking about, but the other two I'll give examples. And then which I will be talking in more details is that there is the so-called weak measurement, as I said, which can amplify this spin orbit photonic effects. And I will give example of weak measurements first, and then I will talk about these metamaterials and how weak measurement also can be used on the metamaterials. So let me just quickly introduce this concept of weak measurement. Weak measurement, of course, is a quantum mechanical concept. When we do any measurement, we couple any measurable observable to a device or a pointer, right? And we measure the eigenvalues of this observable through the deflection of the pointer. So this coupling Hamiltonian can be written like this. I have written Hamiltonian minus gamma q, and a q is some canonical variable of the pointer. It can be position, momentum, it can be time, frequency, something like that. Okay, and a is the corresponding observable. So this pointer, of course, not like a delta function. It can have a width. Let's say it have a Gaussian thing, and I have written it in the q is the canonical variable, and its conjugate space is the momentum space. So I have written this wave function in momentum space, and there is also this states. That means this observable A can have in any of these states with eigenvalues A1, A2, AN, etc. So when you couple this observable with the device or pointer, they evolve. They go through a unitary evolution, and eventually the pointer will be, after evolution, will be something like this. So it will be in the momentum domain is a Gaussian, and it will be shifted depending upon the eigenvalues and of course the coupling coefficient. Usually when we call a strong measurements, so these pointers will be shifted with respect to each other depending upon the eigenvalues, and you can well resolve them, and from there you can actually measure the eigenvalues. So that is a usual measurement. But there is also the other limit, what we call the weak measurement, where this coupling gamma is very weak. In this case, they are not separated. That means this individual, if you see the pointer profiles, so the width is much larger than the separation of the eigenvalues. And this is the so-called weak measurement limit. So in this limit, of course, you do not get much information, but at the same time, it also does not part of the system. That is one advantage. But what Aronov, Albert, and Weidman showed in their seminal paper is a very interesting thing happens when you do a post-selection. So that is what we call the weak value amplification, weak measurements plus post-selections. Now, if we post-select the system in a state like psi f, which is now written as, let's say, alpha n prime an, so alpha n can be complex, of course. So then they showed by simple algebra in the same way that if we couple the device and the observable, the device state evolved after post-selection, it will become something like this. It is something similar to what we had for the eigenvalues also, like in the momentum domain here also. But now it is shifted by not the eigenvalues, by something we called the weak value AW, which is defined like this: psi f A psi in by psi f psi in. The numerator is like the expectation value, but of course psi f and psi in are not the same. They can be different. And you see here that if psi f and psi in, that means this denominator is the overlap between the pre and the post-selected state. If that is very small, the AW can become very large and can be unbounded, right? So when psi f and psi in is 0, of course, this limit breaks down. Psi f psi in 0 is the exact orthogonal pre-post selection. So interesting thing, of course, happens when you have near orthogonal pre-post selection, and this quantity, small quantity, will refer to as epsilon also. So when epsilon is small, then you can see that it is a very large weak value. And this is what we know as weak value amplification. So the value can become outside the range of the eigenvalues. So using this, you can actually amplify a very weak effect. That's what we will show you in some examples of that. Of course, it has a bound in the so-called linear response regime. That it has a bound of this weak value. Another interesting thing of this weak value is that unlike eigenvalue, it can have basically complex values, right? So real weak values will be in, let's say, in the Q domain, that is in the position domain, and imaginary weak value will be in its conjugate domain, in momentum domain. Okay, so what is interesting is that, so this weak value can be actually interpreted like an interference effect. So it's a manifestation of interference. So simply it can be thought like that. For example, the example I was giving, let's say you have a two-state system, like you have a Gaussian pointer. Now these two states are slightly shifted with respect to each other. So that means the pointers are slightly shifted, which is the so-called weak interaction. We can think of like that, let's say the spin Hall effect, I was giving an example. The two modes are left and right circularly polarized light. So if they are slightly separated with respect to each other, so that is we call a weak effect or a weak interaction. Slight separation means the separation is much weaker than the width of this pointer. And then let's say now if I take a linearly polarized light, then it has both the components of left and right circularly polarized light. And then I post-selected a near orthogonal. For example, I choose a 45-degree polarized light, and then I choose minus 45, but not exactly minus 45. Epsilon angle, very small angle off from this minus 45, then it will be like a near destructive interference. That means it is A minus B, but it is not exact destructive interference because you are making epsilon off from that. And that leads to a very large deflection of the pointer, and which is this weak value A by epsilon. So this interferometric philosophy makes it realizable in classical optics, and I'll give example of that. So the first thing that we did, I'll just quickly give an example of the spin Hall effect of light that I was referring to. So the spin Hall effect of light is rather weak. So it provides a weak coupling between the pointer, that means the Gaussian spatial mode. If you take a Gaussian beam, the spatial mode is the pointer here. It gives a weak coupling between this pointer, Gaussian spatial mode, and also if you change the polarization as a system state, so it gives a weak coupling between the spatial mode and polarization. And you can do a pre-selection in one of the linear polarization, and you can do post-selection in near orthogonal, as I was just referring to. That let's say if you choose at plus 45, your near orthogonal is minus 45, so you'll give just plus epsilon and minus epsilon away from there. So this leads to a very large amplification of the spin Hall effect. Typically, I was saying that the spin Hall effect is in the sub-wavelength domain, that is lambda by 2 pi in nanometer. You cannot detect using CCD, but using this simple philosophy, we could amplify that. So this is a simple video I show you. So if you see that as epsilon becomes close to 0, there is a large jump. So that is the amplification of the spin Hall effect of light. In fact, using this approach, we could amplify spin Hall effect of light by almost 1,000 times, and we could also go beyond the so-called Aronoff, Albert's, Bedman's linear response regime, which I will not discuss here. But this is just an example where weak value amplification is done to amplify the spin orbit photonic effect or spin Hall effect of light. Borrowing this philosophy, what we did next is that we introduced this philosophy in the context of plasmonics. So weak value amplification using spectral response of Phenol resonance as pointer. So this is what I will of course discuss what is Phenol resonance. So this offered tunability of Phenol resonance in a hybrid metamaterial, which is basically I will tell that this plasmonic metamaterial. Here, unlike the previous case, the conjugate parameter space is not position and momentum but time and frequency because it is in the wavelength domain, and I will explain this. So let me just quickly give what is Phenol resonance. Many of you may be familiar with this, that the conventional resonance are the Lorentzian one, like this we see here, and it's a perfect Lorentzian with the width is gamma, and the central frequency is omega 0. But when such a discrete mode interfere with a continuum means it's a very broad kind of resonance, then what happens is that you get an asymmetric line shape, just like this I have shown here, this yellow line. So this asymmetric line shape was observed by Phenol, and accordingly it is known as Phenol resonance. The asymmetry is dependent upon the so-called Q parameter or the asymmetric parameter. It is defined like this, the line shape Q plus epsilon square 1 plus epsilon square. So this epsilon is the reduced energy omega minus omega 0 by gamma by 2. So you can see there is a dip here which is called a Phenol dip at a frequency omega 0 minus Q gamma by 2. Let me just show you that how it varies the line shape as a function of Q. You can see that it is perfect Lorentzian shape for Q is equal to 0 and infinity. For any intermediate value of Q, you have the asymmetric shape. So this kind of Phenol resonance in the optical domain is very interesting, and they have many applications, particularly for sensing, color display, and many other applications, and where it is desirable that you can have a tunability of Phenol resonance, so that you can have multi-sensing platform, you can have robust color display, and so on and so forth. So these weak measurements or weak value amplification we used for achieving such tunability. So we modeled such a Phenol resonance using simple classical model, as I was saying, that if you can think about the interference of the two modes. So one is of course a very narrow mode. So we all know that there is a phase change of pi across the resonance frequency of pi like that. So narrow mode will have a phase change like that, and the broad one will have a very slow thing. So in one side, these two modes will be in phase, and the other side they will be out of phase. So here they will be destructively interfering to give you the Phenol dip. And we modeled it, and you can see here, according to this model, that if you have at the Phenol dip, you have an exact destructive interference. The phase difference is pi, and the amplitude ratios of these two modes are also unity. So therefore, you have perfect cancellation of the intensity. So this is a phenol. So what philosophy we used here is that we made a weak coupling between this spectral response of photoresonance and the polarization. For that, we tailored weakly anisotropic photoresonance, and then we did pre and post selection just like we did it for the spinol effect of light using polarization state of light. So using this philosophy, you can say that if you want to have a weak coupling between the spectral response and the polarization state, so that is what we say that weak measurement using asymmetric spectral response of photoresonance as pointer. So weak coupling means the two resonance frequencies omega 0 x and omega 0 y for two different polarizations, they are only slightly off from each other. So the difference in the frequency is 2a, which is less than the gamma, that is width of the pointer, that is width of the line set. That is exactly similar to what I was referring to in the case of the Gaussian spatial mode. And then, of course, this additional criteria is that the qx minus qy, the asymmetry parameter difference would also be small. So this is what we call the weak coupling between the polarization, which is a system, and the spectral response. So this kind of system we could realize in a special kind of metamaterials, which is in a wave-guided plasmonic crystal. So this we fabricated using E-beam, electron beam lithography. So just to quickly say that it has two things. One, that you have some gold disc or gold grating array on top, and below that you have an ITO layer. So this ITO layer supports waveguide like this, and this metallic this thing grating, or you can use something else also like periodic array of disc, etc. So they support surface plasmon or localized plasmon resonances. So localized plasmon resonances are broad, so they are lossy, and this waveguide resonance is very narrow, so they kind of mimic the two discrete and the broad modes for the continuum here, and they give rise to photoresonance in this kind of system. So these are the kind of things that we have fabricated. As I said, that it not necessarily it is grating. We have fabricated disc array, nano disc array, nano ellipse array. And what is important here is that by tailoring the geometry, you can actually tailor the photoresonance here, right? So that's what we also, before we fabricated this, we did some simulations using finite element method to determine what parameter you should choose to have the desirable effect. So this is a typical example of Phenol line shape in this kind of wave-guided plasmonic crystals. Now, how to experimentally realize this concept of weak measurement? For that, we use something called Muller matrix measurements. Muller matrix is the transforms the Stokes vector describing the polarization properties of incident light to the Stokes vector of scattered light. It contains complete information about the polarization properties of the medium. So Stokes vector, I briefly speaking. So this I, Q, U, V. I is the total intensity. Q is the difference in intensity between horizontal and vertical polarization. U is the difference in intensity between plus 45 and minus 45. V is the difference in intensity between left and right circularly polarized light. And this 4x4 matrix contains all the information. So all kind of anisotropic effects can be encoded in this 4x4 matrix, which is Muller matrix. What is important is that such a matrix can be measured. And we actually developed a system, first a free space system. So this kind of matrix, which is a 4x4 matrix, it requires 16 measurements. So what you do is that so-called, what we call it, a polarization state generator unit comprising of maybe a polarizer and a wave plate, and you can have a fixed polarizer and wave plate can be rotated to 4 different angles to generate 4 elliptical polarization states. And in the same way, you can analyze it 4, so you have 16 measurements. You can take image, you can take spectra. In our case, of course, here you will take spectra, and this is coupled to a microscope, which is a dark field microscope. So the dark field microscope is important here because it enables basically recording of the scattering from the nanostructures, which is very weak. So this is, of course, you know that in a dark field microscope, unlike a conventional microscope, you have an annular aperture here, which gives an annular beam. Direct light misses the objective. So only those lights scattered by the nanoparticle or nanostructures is collected by that. So this enables us to measure or perform the weak measurements on the plasmonic nanostructures, or in this case, the wave-guided plasmonic crystals. So how did we do? So we, of course, recorded the Muller matrix as a function of lambda or energy I have written. And then pre and post selection can be done using polarization states. That is, in this case, intensity-based Stokes vectors. Two different schemes we used. One is scheme 1, where, as I said, that the input state was, let's say, 45 degree. The Stokes vector is 10, 10, and it is post selected. Orthogonal will be minus 45 degree, which will be 10, 0, 0, 10, minus 10. but it is not exact orthogonal, but epsilon off from the orthogonal. So the state is 1 plus minus sine 2 epsilon minus plus cos 2 epsilon 0. So in this case, what we see, we call it a real weak value amplification, and the shift of the pointer happens in the frequency domain or in the wavelength domain. Therefore, there will be a shift of the resonance frequency. So this is one scheme. And the second scheme, what you do is that you do now not a post-selection is not using a linear polarized light. So pre-selection is at 45 degree. Now post-selection is minus 45. Now the angle is not made off. So you make it slightly elliptical. So what you do is that you put a wave plate, and the wave plate angle is, if it is aligned along the direction of the polarization, that is 45 degree, then it is perfectly linear. But if you make it slightly off, epsilon off from that, then it becomes elliptical, slightly elliptical. And the state becomes 1, 0 cos epsilon plus minus sine epsilon. So this is the post-selection state there. So this actually yielded so-called imaginary weak value amplification. As I was mentioning earlier, that weak value can have both real and imaginary values. So this is in the conjugate domain. So that means it is in the frequency domain. Now it is in the time domain. So this conjugate domain in this case, because we are recording spectra, will be manifested as a change in the width, that is width of the resonance. That's exactly what we did. So before that, of course, we had to tailor the weak coupling between the polarization and the phanospectral response. For that, we had to tailor the plasmonic crystals parameters. As I said, that these parameters can be tailored such a way that the spectral response for the two orthogonal polarization, X polarization and Y polarization, are similar and indistinguishable. You can see that experimentally recorded phanoresonance spectra for X and Y polarization are almost similar. So therefore, they satisfy the weak coupling criteria. So what is that? There is a weak coupling between the spectra, degree of freedom, and polarization. So that if I have, let's say, this horizontal and vertical polarization, you cannot resolve it. So that is what we said, that a weak coupling. And now you do two kind of post selections. That is one for the real weak value amplification, where you will get the shift of the frequency. Another for the imaginary weak value amplification with elliptical post selection. So you will see the width will be changing. So exactly what we observed. So this is what the experimental results. You can see beautiful tunability of the line shape. You can see it varies as you change epsilon. There's a large variation of the spectral line shape, and it followed the weak value criteria of cot epsilon. As I said, that it varies 1 by epsilon or cot epsilon. Similarly, in the imaginary weak value amplification, there was a broadening of the spectral line shape, no shift as such in the peak position, but broadening, which is like a time domain shift, because broadening means change in the effective gamma width. So that means effective decay constant. So this is what we could achieve, and you can see that there is a beautiful tunability of phanoresonance using this kind of polarization measurements, and this allowed, of course, this enabled spectacular tunability of phanoresonance. It could also amplify and detect small weak anisotropy effect, and it can also help in resolving extremely small spectral shift. So these may enhance phenol-based applications in multi-sensing platform, filter, color displays, etc. In general, this may open up a completely new paradigm of weak value amplification using spectral line shape of resonance in wide class of spectroscopic system. So I'll give you another example of this weak value amplification, which is slightly different from there. So, but of course, the system is same, which is magnetoplasmonic crystal in this case now. In this ITO now we replace by a magneto-optical layer. So this magneto-optical layer has an additional thing, magnetic thin film. Is there a magneto-optical effect or Faraday effect? It's a very small polarization rotation. Otherwise, you cannot detect. So what we did here is the same system. It will also give phanoresonance, but with a very small Faraday effect. Unlike the previous case, here we use polarization state as a pointer. In the previous case, of course, the pointer was a spectral response. Before that, in the spin hole case, the pointer was a special Gaussian mode. Here, and in that case, polarization was the system, and we did pre and post selection using polarization. But here, what we did is that we use polarization state as a pointer, and this is the philosophy. So, as you see that I said that phanoresonance gives you an interference effect between the discrete and the continuum mode. So, you can think that in this case of the wave-guided plasmonic crystals, magnetoplasmonic crystals, one is this waveguide mode. This waveguide mode has a small polarization rotation effect, and the plasmon mode background has no, it is isotropic in it. So this is a very weak polarization effect between them. So this is a weak coupling between the spectral response and the polarization degree of freedom. Now here pre and post selection, as I said, that weak value amplification can be interpreted, near orthogonal pre-post selection can be interpreted as near destructive spectral domain interference between the two modes. Here it exactly happens because, as I said, that near the Fano deep, exactly at the Fano deep, you have perfect destructive interference between this narrow mode and the continuum, as I said. So here the two amplitudes will be the same, phase difference will be exactly pi. Now, if you slightly go away from the phenodic position, you are mimicking the near destructive interference phenomenon. That is to say that you are making slightly small phase offset from pi, slightly small amplitude offset from equal amplitude of the two modes. And this is what, as I discussed earlier, that weak value amplification can be interpreted as near orthogonal pre-selection, pre-post selection can be interpreted as near destructive spectral domain interference. Here it is inbuilt near destructive spectral domain interference, here inbuilt pre-post selection, where you do not have to do any external pre-post selection. And this therefore we named as natural weak value amplification. The effect is that this weak Faraday effect is amplified to a large extent around this near destructive interference. So this is what we observed, that if you have the phonoresonance spectra like this, you can see that green line. So this is the spectral dip where exact destructive interference takes place. If you slightly go from this in a wavelength domain from this side or that side, you see a very large amplification of the Faraday effect. You see this blue line. So the Faraday rotation was otherwise small, but it is amplified near this Phenol dip, which we interpreted as a basically natural weak value amplification of Faraday rotation. We of course observed natural weak value amplification of both Faraday rotation and ellipticity also, because I said that it can have both real and imaginary weak value amplification. So this was the corresponding theoretical weak value fit. You can see very beautiful matching. Also the ellipticity also had this kind of amplification, imaginary weak value amplification, and they followed like this. And a psi will follow cot epsilon or 1 by epsilon. As I said, the weak value amplification is a hallmark is it will vary as cot epsilon or 1 by epsilon, and the ellipticity also varies as 1 by epsilon. So this was of course experimentally observed by other group, but what we interpreted is that this is a natural interferometric weak value amplification of Faraday effect. So these are two important examples of weak value amplification, and we have been actually using this kind of weak measurement in different other scenarios. Now in the last part, I will talk about very briefly about some of our recently observed novel spin orbit photonic effect and some device concept that we have generated based on these effects, right? So this is quickly saying that we have been talking about spin orbit interaction, that is a coupling between intrinsic spin and intrinsic OM, or intrinsic spin or an extrinsic OM. Here what we call this is an orbit-orbit interaction. So this is the first experimental observation of orbital Hall effect of light. So orbital Hall effect of light is basically a coupling between the intrinsic orbital angular momentum and extrinsic orbital angular momentum. So we have observed in a very simple geometry in a partial reflection from a right angle prism, and what is important that we have shown that it is completely independent of spin. So to do that, we generated randomly polarized light and radially polarized light. For generation of randomly polarized light, we used a special light modulator. For the generation of radial polarization, we used a SOA plate, combination of a SOA plate and a polarizer, and we observed orbital angular momentum Hall effect, that is orbital angular momentum dependent shift of the beam trajectory, which is completely independent of spin polarization of the effect. And this is what we experimentally observed, and the corresponding simulation also showed for random and radial polarization beautiful shifts, orbital angular momentum dependent shifts in the beam trajectory. So this is a new one that we have observed. This may also have various applications in OM sorting, etc., which may be pursued later on. So this is another interesting effect that we observed is a spin selective random scattering modes in disordered anisotropic medium, that is spin Hall effect of light in random medium. Here also the random medium we created by giving random phase gradient in the spatial light modulator, and we could tailor the dynamical phase and geometrical phase such a way that for one polarization you have the random spin split mode, for the other polarization it was maintaining the usual shape of a Gaussian beam. So this is also another interesting effect that we observed. And we have been, of course, working on this so-called transverse spin and Bellin-Fenton spin momentum. So we have shown that this transverse spin can arise in scattering for plasmonic nanostructure also. So I'll not go into the details of that. So now another interesting device concept we have recently shown. As you see that when polarized light propagates to an anisotropic medium, you have a geometrical phase. So if you have a space-varying anisotropy, you get space-varying geometrical phase. The opposite is also true. If you have a space-varying polarization pass through a homogeneous anisotropic medium, you will generate a space-varying geometrical phase. So this gives you a clue that if by some means, if you measure the space-varying geometrical phase, you can actually measure the space-varying polarization using a single shot measurement. So this is what we did here using a interferometric configuration. We generated, of course, in this case, the space-varying polarization using SLM, but it is true for any arbitrary space varying polarized light coming from distant sources, and this actually using an interferometric setup, we could quantify the space varying geometrical phase, and from which we could actually measure the space varying polarization of light using a single shot measurement. Usually we will require Stokes vector measurement, multiple measurements to do that. So this might also be turned out to be useful. And we also, as I said, that we have been playing with geometrical phase at the nanoscale. So we have been developing various meta surfaces like this one I've shown here, that you have a grating, the grating orientation rotating as spatially varying. So that orientation gives you space varying geometrical phase. So this kind of meta structures we are making using our E-beam lithography system to actually tailor the light at the nanometer length scale. So they also have many may have many applications in control and manipulation of light in the nanometer length scale. So this is something which we have latest developed. So this is borrowing the concept from the interferometric philosophy of weak measurement. So this is a new concept of weak value polarimeter. So again, we use a Mach-Zehnder kind of interferometric setup. We provide a weak coupling between the polarization and the path degree of freedom of light, just like we are seeing in the case of Canon Resonance. By this means, we can actually amplify very small polarization anisotropy effect. So this can turn out to be very useful for detecting very small polarization anisotropy effect. We have shown that the conventional polarimetry sensitivity can be enhanced manifold by using this kind of weak value amplification. We named it as weak value polarimeter. So these are various kind of, as I said, that meta surfaces that we have fabricated using E-beam lithography, and we have been studying many other effects on spin orbit photonic effect in this kind of meta structures. And our aim is, of course, to develop spin orbit photonic meta devices and weak measurement meta devices using this kind of systems. And yeah, thank you for listening. And of course, I will be happy to answer questions in online sessions. Thank you very much.